So today, I just kind of want to go over Chapter 2 in general, I'll go over any Wiley questions you guys have. Now, I just covered 2.6, so you might not have had too much exposure to Wiley on 2.6. So I can pull up some of those questions. We can do them in class. I'll talk about where students kind of go wrong. Another thing I want to show you, your resources you have available to you. So you sign in a Blackboard, you probably just go to the Calculus link tab and then find everything that I post. There's a Calculus resource page that was developed about 4 years ago with some resources. And really the only thing that has too much weight is the old final exams. And I feel like it's never really too early to start preparing for the final exam. The final exam is 25% of your grade, but on top of that, it can also replace your lowest exam score. So 25% of your grade, and then it can replace 10% of your grade for potential to be worth 35%. So a lot of students, towards the end of the semester, especially the spring semester, it starts getting nice out. It's really, really hard to study for calculus. So if you study a little bit along the way, you're in a lot better shape towards the end of the semester. So really this is the main thing on this old final exams that you can find. And there's 8 old final exams there. I'm actually going to contact some of the previous coordinators that taught calculus and see if they have some that aren't posted, just so you can have more practice. 4 of them have solutions. So if you just open just a random semester final exam, you can kind of see, you should at this point be able to do the first 2 pages, maybe even part of the 3rd page.
So kind of in order of how you learn them?
Yes, it is. It's in the order of Chapter 1, Chapter 2, Chapter 3, so forth. So, you know, like, you should be able to evaluate the first 2 pages for sure. Maybe we haven't quite got to what the derivative of ln of x is, so some things like that one part you won't know how to do, but you should be able to find the derivative of this function, this function, this function, this function, and more so you should be able to find the second derivative of it. Now this ln of x, we haven't talked about the derivative of that yet, so and e to the x we haven't talked about yet, but you could do this one. We talked about the quotient rule. You could do this one because we talked about the chain rule. Again, with ln we haven't talked much, so really the first 2 pages for sure, and maybe the 3rd one, picking and choosing some of the stuff you know how to do. And if you start getting kind of the idea of how the final exams are paced and what's always tested, like generally there's something like a constant over something going to 0 somewhere in there. The definition of a derivative is probably on 95% of them. So we've talked about 2.2, and then we went to 2.3 and 2.4, and we learned techniques of differentiation. So everyone in here should be able to tell me what the derivative of 3x squared minus 1 is. What's the derivative of 3x squared minus 1? 6x minus 1, right? That's a 10-point problem. You know. However, where you're getting the points is the definition of the derivative. The definition of the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. So plugging in x plus h to this function minus the function over h, that's where you're getting the points. Notice, no other formulas for derivatives may be used in this problem. So if you're just using the techniques of differentiation, you're not going to get any points for that. You want to show the limit. However, you can check yourself, right? And that's always a good thing. When I do the limit, do I get 6x minus 1? Or do I get something else? Because if I don't get 6x minus 1, I did something algebraically wrong before. I want to find that so I get my full 10 points here. 20 point, or at a 200-point final, 10 points, that's 5%. So that can be a difference between, you know, an 85 and a 90 on the final. Which if you think 35% of your, it can be, can add up. So you want to make sure the wording, you understand the wording, what they ask you to find. Things like this. Almost always there's the equation line find the equation of the tangent line. Now, we haven't learned how to do implicit differentiation yet, so you might not be able to do this problem. But if you just look at another semester's, you can kind of...
Just so the answer tries to
The work, yeah. So, here we go. You should be able to do this one. You know, consider this function, find the equation of the tangent line to the function with the x-coordinate 1. Use slope-intercept form as your final answer. You guys should be able to do that, right? And this is on a final exam, 10 points, 5% type thing. Consider the derivatives. Do not simplify your answer. So you should be able to do this derivative, this derivative, this derivative, but they want you to find the second derivative and then plug in 0. You should be able to do that at this point. So really here, the first 4 pages you can do. I think, question?
Is chapter 0 included in this?
Chapter 0 is not included on the final exam. However, we will get to where we will talk about if a function is increasing or decreasing. And the way you evaluate that, you need to find the derivative and set it equal to 0. So if I find the derivative here and set it equal to 0, I have a quadratic. So I'm solving when the quadratic equals 0. So that's really chapter 0, right? But it has meaning. So they're not going to say, solve this expression. You're going to have to do that within a problem that has more meaning to Calc 1. So it will definitely show up, but it's not going to be explicitly simplify this. It will be simplify this within this. That's not asking you to simplify it. Question?
The definition of a function problem that you showed us,
Mhm.
that's essentially the same as the instantaneous rate of change, too, right?
Yes. The definition of the derivative, and I don't know if, yeah, the definition of the derivative gives you the instantaneous rate of change at any point in time, yeah. So if you look, a function here that says find the equation of the tangent line. I think I've given you guys one of these before, so you know all your main points are given. You have your x value, you have your y value, and then you have your slope at your x value. And so you can plug that y minus y1 equals your slope, quantity x minus x1. This is 5 points, not as much work done. Find the instantaneous rate of change of y with respect to x at the point x equals 4. So you could just find the derivative, and that means the instantaneous rate of change. So sometimes they might word it like that. Find the instantaneous rate of change, and you need to know, that means find the derivative and plug in the point.
Will there any multiple choices?
There are generally multiple choices, and just like on the first exam I gave you, they're pretty much you get them all or you don't. So in the case where you're off by a negative, maybe here if it's plus infinity or minus infinity, these are 6 points each. So if you're off by just that negative, you lose all those 6 points. So you really want to make sure you understand here, the limit as x goes to 1 of this function goes to, is it 1/2? That only works when you're looking at the end behavior, right? Because a lot of you, mentality-wise, you're saying, okay, I take the highest and I get x squared over x squared cancels. That only works when x goes to infinity. So here I need to plug in 1. And so, right, I mean, there's only a few choices we have here. So if we plug in 1, we get 0 over 0. But I need, if I plug in 1 and get 0, and I plug in 1 and get, that means 0, x minus 1 is a factor. So I can pull out an x minus 1, so I have an x plus 1 on top. So that would give me 2 on top. And then if I pull out a 2x, I have x minus 1, right? So the x minus 1 cancels, and I have 2x. So I have 1. 2 over 2, right? Right. So if you just said, oh, 1/2's not an answer here, so that kind of saves you. But majority of the time, there is an answer that looks like if 1/2 was here, probably half the people would miss it simply because they're like, oh yeah, I got this. So be a little careful of that, especially when we get, we've only got a quarter way through the course, so by the time we get to the end, sometimes the stuff's like, look at it and just, make it and not think too much. So
So if it
it was 1 over 0, though, it would be does not exist.
You have to be careful because 1 over 0 can be infinity or minus infinity depending on if it's going 1 over something
It was
going.
like x as it goes to 1, and ended up being like a constant over 0.
If I think of h going to 0 of 1 over the absolute value of h, that goes to positive infinity. But if it was the limit as h goes to 0 of 1 over h, does not exist. Because the limit on the right and the limit on the left goes to infinity and minus infinity, so the limit doesn't exist. But if it was 1 over h or h squared, it's going to go to infinity. So that's a little something you have to be careful. Just like the one on the quiz, or the one on the first exam I gave you, it was a negative constant over something going to infinity, and it was either going to infinity on the right or sorry, going to 0. So it's either minus infinity or plus infinity, and a lot of you guys switched those because you were a little concerned about this constant on the top, if it was positive or negative. It was minus 3.
Which question on the?
I think it was on the second to the last page. No, I was right. The second page, the top, this one here. So yes. Here, this example is kind of what I talked. What's the limit going to go here? I'm approaching 1 on the right. How many people say plus infinity? How many people say minus infinity? Okay, so I'm on the right side of 1, so it's like 1.1 or 1.01. If I take 1 minus 1.01, I'm positive, right? So I'm going to 0 but positive, and 1 over something going to 0 goes to positive infinity. So the correct answer would be positive infinity. Right? And draw a number line and see. And plug in a number to see if it's going to be negative or not. I have 1. If I'm on this side, I look like something like that. 1 minus something. Oh, so did I do that wrong? Yeah, 1 minus something like that. See, it helps. 1 minus something like that, I get a negative number. 1 over something going to 0 goes to infinity, but then I'm negative. So the correct answer is negative infinity. So yeah.
I just felt so wrong.
Sometimes that happens. So yeah, a little bit of, sorry, negative infinity. But be careful, because what if it was going to minus negative 1 from the left and it was 1 plus x? You have to be very careful with this. Draw a minus 1 if I'm on the left, or if I'm on the right. Let's say if I'm on the right. Then I look like minus 0.99. Right? So you can't just say, oh, if it's on the right or if it's on the left, because you have to be careful if it's negative or positive. So understanding a constant over something going to 0 goes to infinity, and then be very careful with your negatives. There could be a negative on top and a negative on bottom that cancels, just like the second page on your exam. The first problem on the second page of your exam is like. And then that shows up here, and the correct answer is negative infinity. So sorry for any of that confusion there. Negative infinity. So if you just, made, going through your head and didn't write anything down to check yourself and put positive infinity, that's 6 points. So we talked about doing a problem like this before. Find the value of a that makes it possible the function is continuous everywhere. So we're going to take the limit of the left, the right, and the value of the function.
That was the question on the test that I switched them.
Mm-hmm.
This said which one's to the left and which one's to the right.
Yeah.
I just kind of took a shot in the dark.
So here, like the one that said right, the set up the limit on the left and evaluate the set up the limit on the right. Here, it doesn't matter too much if you switch them, as long as you know that, what is the value of the function at minus 1? Negative 9. Right? Because if x equals minus 1, I use this equation. Minus 1 cubed is minus 1. Minus 1 minus 8 is minus 9. So I'm going to take the limit on the left and the limit on the right and set it equal to minus 9. So if you use the other one, you're not going to get the right answer there. You're going to get the value of the function is a or something.
So you put like 1 plus a equals -9, right?
Correct. So yeah, the algebra there is pretty straightforward to solve for a. You might have like a quadratic or something, but again, being able to solve for quadratics pretty straightforward. Besides not having the derivative of ln yet, you should be able to do a few of them. You should be able to do this one, the quotient rule, the derivative, the derivative at 1, and then the derivative at the second derivative at 1. So given this function, you should be able to differentiate it at this point, plug in 1, differentiate again, and plug in 1. Anyone? So generally the first 3 pages, like I said, pretty safe. Yes, differentiation, yeah, differentiate the function means find the derivative.
Are we required to write the steps, like all the first one times, or?
We don't want you to simplify, so we understand what you're calling the first function, and we say, okay, if you write 6x times cosine x, we know that you're saying this is the first function and the derivative is 6x. We can see that, and we grade it part by part. So if you take the derivative of this wrong, you're only going to miss the point for taking the derivative of that wrong. So you don't have to write out anything, you just find the derivative. Because really there's not a lot of room here. And we want you to put pretty much everything here. So it's going to be the derivative of this function, holding cosine, plus holding the first function, the derivative of cosine. And it doesn't matter what order you write that in. We can account for that. So you should be able to, 6 points, you can find this one, the derivative of this function. You can find the derivative of this function, theoretically now, right? So do you guys see how right now, if you just start studying for finals, by the time you actually are ready to take the final, you've gone over the finals and pretty confident at the level that you need to perform on to get whatever you want in the class. So does everyone understand how to get to this resource page? It's from the home page of Blackboard, so you won't go into calculus specifically. You'll scroll down to My Organizations, and it will say Organizations which you're a member. Mine says Assistant, but click on that, and then you'll click on the Calc 1, and it's about the middle of the page, and it gives you old final exams. There's links to Dr. Delaware's videos, however, it just links you to all the different lectures, and it doesn't tell you what is being covered in what lecture, so. Okay, any questions on Wiley? Oh, I just exited. Question?
Did you do on 2.5 the one with the like pies?
The 6x cosine something. Find the equation of the tangent line at x equals pi?
Yeah, I think that's what it was.
Yes, I can attempt to do that one. 2.5?
Yeah. It's like the third one for the bottom. Yeah.
Okay, this is kind of a good approach to a problem where you can think about it or you can graph it and kind of see what's going on, but you should also be able to do it by using the definition of the derivative and plugging pi. So you're writing the equation of the tangent line of y equals x at the following x values. So we have these multiples of pi. So 2.5, number 26. So we have y equals sine of x, and we want to find the equation of tangent line at part A, x equals 10 pi. My pen's somewhat dying on me. So the graph y equals sine of x. So I have 2 pi, 4 pi, 6 pi, 10 pi, so forth, right? It's periodic, and the period's 2 pi. So at 10 pi, the equation of the tangent line is going to be the same as at 2 pi, right? So I could go in graph, so this would be 2 pi, this would be 4 pi, 6 pi, 8 pi, 10 pi, right? So 2, 4, 6, 2, 4, 6, 8, 10. So this would be 10 pi. So I'm looking for the equation of the tangent line at this point. So what am I expecting my slope to be? Positive. So that should be just some kind of reassurance. So what is the derivative of sine? Cosine. And I evaluated at 10 pi. What's cosine of 10 pi? What is it? 1. Good. So this gives me my slope. And then I need a point. And my point is going to be 10 pi, comma, sine of 10 pi. What's sine of 10 pi? 0. So now I have a point and a slope. So I have y minus 0 equals 1 times 10 pi x. X minus 10 pi. So I have y equals x minus 10 pi. Do you guys see that? Sorry, it's a little messy. So this is my equation to my tangent line at this point.
How did you know it was 10 pi 0?
This is x, which was given, and then if I plug in 10 pi to my function here is going to be sine of 10 pi. Right? My original function is sine of x. So if I plug in sine of 10 pi is 0. Question?
And the way you got the 1 is if you put 10 pi as cosine.
Correct. The derivative. Because cosine's the derivative of the function, and if I plug the value of x in the derivative, I get the slope at that point. So I think the next part is 5 pi. 5 pi. So what is going to be the equation of the tangent line at 5 pi? So at 5 pi, so I have 2 pi, 3 pi, 4 pi, 5 pi. My slope's going to be minus 1. So, sorry, my slope's going to be minus 1. But my y-intercept's going to be related to my tangent line being at 5 pi. Here, my y-intercept, you would think it to be negative, which it is. So that's kind of nice. You can see how like a visual representation just kind of can give you some idea if you're close. However, not all functions you're going to be able to graph and think about how the tangent line is going to work. So here, we've already found the derivative, cosine of x. If I plug in x equals 5 pi, I get minus 1, right? So what's my point?
Minus 1, 0.
What is it? 5 pi, comma 0. So I do the same thing. Y minus 0 equals minus 1, x minus 5 pi. So I have y equals minus x plus 5 pi, which is which is what we would expect, because we would expect our y-intercept to be positive. Here we would expect our y-intercept to be, in the previous example, we would expect it to be negative, which it is. Any questions on that? Any questions on equations of the tangent line? I'd say that shows up on a final exam 95% of the time, in some form or another. Did you have a question?
I have a question about the graphs of the derivatives. It was on the homework that was due on Monday.
Yeah. So we have 2.1, 2, 3.
2 or 3, I'm not sure.
On Wiley?
Yeah, there was one.
Oh, I was thinking.
I guess any questions, but I just don't really remember how to.
Okay, so let's see. It was probably. Ooh, here. 2.2.
Yeah.
Okay. So 2.2, the problem comes from your book. So there's multiple variations on Wiley. So if we go to the book, we can kind of see some of the variations. And did we talk about this a little bit in this class?
I think so.
Yeah. So you should be comfortable with matching graph it, and you should also be comfortable with just drawing the derivative on top of the graph. So here, anywhere my slope is 0, that means my derivative is going to go through the x-axis at that point. So in these two, my slope is 0 at x equals 0. So this is going to correspond to this one and this one, right? These are the only two graphs that my slope is 0 at x equals 0. Here my slope is some value, right? Here my slope is undefined. Here my slope is 0. I guess this one also has a 0 slope. And then here my slope is undefined at that point. So critical points are going to be something we're going to talk about later in chapter 4. We'll talk about how critical points give us information about the derivative. And it turns out when the first derivative equals 0, that's a critical point. That's a turnaround point on the graph, right? So if it's going from a positive slope to a negative slope, that's a turnaround point. Or a negative slope to a positive slope, that's a turnaround point. So these critical points can be found by taking the first derivative and set it equal to 0. So you can see where the first derivative crosses the x-axis, that's where it equals 0. So you can kind of get the information of the critical points out and then match your graphs. And we'll definitely have more exposure to these types of concepts later on. But yeah, anytime you're given a graph of a function, you should be able to kind of follow it to see what the slope is doing. Question?
Will graphs be on the exam?
The final exam?
Well, that and our next exam.
Our next exam, there'll probably be something about graphs on our next exam. On our third exam, there's a graphing section. And in chapter 4, we talk a lot about graphing functions. And you can see if I get, in chapter 4, applications, we talk being able to analyze functions, being able to talk about concavity. See if it says anything about the introduction in chapter 4. Function analysis is what it's called, and we'll talk about when do we know a function is increasing. Turns out the function is increasing when the derivative is positive. The function is decreasing when the derivative is negative, so forth. It's constant when the derivative is 0 type thing. So we're going to apply being able to take derivatives of complicated functions and then being able to do some analysis to get information from the graph. So in college algebra, you had like the x-intercept and the y-intercept. But other than that, graphing was relatively hard to do, if you remember your graphing section in college algebra. And here, we're going to get more information. In this interval, we know that the function is increasing because the slope is positive. So we know if we have our x-intercepts or y-intercepts, all this information, we just connect the dots. So chapter 4 has a lot to do with graphing functions. And so you'll see a lot more graphing functions in chapter 4. When is the derivative? How does the derivative the derivative of the function, how is that affecting the graph of the function? And so we can get information from the derivative. We can also get information from the second derivative. Second derivative has to do with concavity. Is the function opening up or is the function opening down? We'll get to all that. So you'll see more about graphs later on in calculus. So they definitely show up on the final exam as well. Question?
Could you do an example of a chain rule problem that has like more than 2 layers?
Yeah, so let's look at Wiley. Wiley has some good examples of chain rule problems that have more than 2 layers. So this one really has 1, 2, 3, 4 layers. So let's do this problem. Wiley is very generous the way they let you enter in chapter 2.6. So, I mean, as long as you're correct, if you have 2 times 4 and you don't put 8, you put 2 times 4, Wiley's going to accept it. So we played around with that last class period, and I was kind of surprised how non-simplified they accepted the answer. So So what's the overall outside function? It's not saying cosine of 6. It's saying cosine to the 6th power. So the whole outside function is something to the 6th power. What's the derivative of something to the 6th power?
Times that something to the 5th power.
Very good. 6 times that something to the 5th power. So this chain rule has 1, 2, 3, 4 elements to it. The outside function is something to the 6th power. The next function is cosine of something. Then the next function is sine of something. And then the next function is 5x. The nice thing about the chain rule, it's all multiplied. Something, the derivative of the outside, evaluated of the inside, times the derivative of the inside, times, and so forth, right? The derivative of the inside would be the derivative of the outside, evaluated at its inside, times the derivative of its inside. And its inside might be the derivative of its outside, evaluated at its inside, and so forth, right? But it's all being multiplied. So it's kind of nice that we can just rearrange it at the end. Now, eventually, I might say this whole function times x, which is going to have to be a product rule within a chain rule, right? So I'm going to have to do the product rule of my overall form, and when I take the derivative of the second function, I'm going to have to use the chain rule. So let's write this one out. So this is 2.6, number 33. Y equals cosine to the 6th power of sine of 5x. So it might help if I write it as cosine sine of 5x all to the 6th power. This is what it means, right? So the derivative of the outside, like we said before, 6 evaluated at the inside to the 5th power times the derivative of the inside. What's the derivative of the inside? Negative sine of 5x. Right? Does everyone see that? Some of you are like, the derivative of cosine is minus sine. So the derivative of the outside would be minus sine, evaluated at the inside. Then I'm going to take the derivative of the inside with the derivative of sine.
Sine 5x
Good. So then I have cosine of 5x
times 5.
times 5.
So based on the first part, like the 6
Mhm.
cosine, is it the derivative of the outside also?
This 6 something to the 5th power is the derivative of something to the 6th power. Right? So this would be the derivative of the outside evaluated at its whole inside times the derivative of the inside. And the derivative of the inside is the derivative of this outside function evaluated at its inside. So you see how you leave the inside alone at each part. So Wiley will accept this. If you do this on an exam, I would prefer you kind of multiply your constants out and put it out front, and then also put the negative out front so I know that you understand it's all being multiplied and it's not this times this. So I would prefer to kind of see it as minus 30, and then you can say cosine of sine of 5x. You could even write the 5 here. Times sine of 5x times cosine of 5x again. Wiley will accept the above, though. Anyone have any questions with that? Yes.
So the outside, I would have thought to just do cosine of 6. So
A lot of students would make that mistake. The outside function is something to the 6th power.
so it's just like if we were to do x to the 6th.
Yes.
And you can do cosine by itself, and you can do x to the 6th by itself. So the outermost would be
The outermost is something to the 6th power. So sometimes students lose this when it's something like this. Let's do this one. This is a product rule, right? a function times a function, but when you take the derivative of one of the functions, you have to use the chain rule. And a lot of students miss one key part of it. So I'm going to give you guys a chance to work this one out, and then I'll go over it with you guys. So I'll give you the chance to see if you're the student that's going to... This is number 27. 2.6, number 27. Plus, yeah, because it's the product rule. So then what's the derivative of this function? You're one of the students. What would it be? Just like it was here, right?
Okay, so that's.
Yes.
Or just one or two.
Yes. Correct. And what's the derivative of this? What's the derivative of the whole inside? What's the derivative of yeah, what's the derivative of sine of 5x? Good. Then, yes. Yes. Nope. So then what's the derivative of this inside? So what's the derivative of that? Well, you've already done that, right? So the derivative of sine of 5x is cosine of 5x. So what's the derivative of 5x?
That's one of the.
Just 5, right? You had it before, right? The derivative of 5x is 5. What's the derivative of this function? And then you need a whole of this function. You're multiplying. Everything's multiplying.
I just started writing now.
And then multiply it by the first function.
This is the really messy version. That's
Just the first
you
function.
have to start the product.
Yeah, well, this function is the first part. Yeah.
I was showing. But yeah, you. So you take the derivative of x to the 6 and times the whole regular one. And then you have x to the
walking
6
around-
times the derivative of that sine squared 5x, and you add the chain rule, the chain rule, the chain rule.
Hold the first function, or the derivative of the first function, hold plus, but then all this is good, but this would be plus. Okay, so here's what I get. Some of the most common mistakes are to forget about the squared, and you lose this sine of 5x when you do that. And then another common mistake is you get so excited you got the derivative of the second function, you forget to hold the first function. So that's another one that some students forget about. So the derivative of the first function, most everyone had this on their paper. Some of you had it multiplied. But remember, the product rule says the derivative of the first, hold the second, plus the derivative of the second, hold the first. So you need that plus in there. And then here, the outside function is something squared, so 2 something to the first power, times the derivative of the something, which would be cosine of the inside, times the derivative of the inside, which would then be 5, and then multiplied by the whole first function.
Sorry, I don't get this. Go to this. 2 sine
This?
5x. Oh, yeah.
This is whole the derivative of sine squared of 5x. So this whole thing here is the derivative of this function here. So if I take the derivative with respect to x of sine squared of 5x, I get what I have here. So so this is a really composition of 3 functions. The outside function is something squared. The middle function is sine of something, and then the third function would be the 5x. So if I plug 5x into sine of x, I get sine of 5x. If I plug that into x cubed, I get sine of 5x, or sorry, squared. I get sine of 5x squared. So I bring down the 2, evaluate the inside to the first power, times the derivative of the inside, which would be cosine of 5x, times the derivative of its inside, which is 5.
Minus x.
Hold the first function, yeah.
Does the order matter here? So I did 2 sine 5x times 6 to the 6. Then I continue.
You said 2 times 5?
No, 2 sine 5x the same, but then times x to the 6. I hold the second one. I mean the first one after that.
Do you have this cosine of 5x in there?
I have it, but
So
after
that's a
x to the 6.
function within a function within a function.
Wiley's
You have to
going to
start
accept
with
that. If you have things, it doesn't matter the order when you multiply them. A times B is the same as B times.
But then you have to talk about the derivative of the inside.
On
That
an
is
exam,
sine of 5x here.
I'm going to want you to
We just
simplify
gotta
at
talk about the
least
derivative of the inside, which is 5.
to this level. So it's confusing to me if you put in 6x here because I don't know where that came from. Since I follow your work, I mean, you can flip these two, no problem. But here I'm saying, okay, derivative of the outside value of the inside times derivative of the inside times derivative of the inside. If you throw the 6x in here, I'm going to be really confused. Hopefully, if it's correct, I can say, okay, this is correct. I don't know why they did this. But if it's correct type thing. But you might give me a headache reading it, thinking, I don't know why he put his x to the 6 here. And is the x to the 6 part of the sign if you lose parentheses type thing? So if that makes sense. Wiley will accept it if it's right. So if you don't multiply the 2 times 5, Wiley's still going to accept it. But I prefer you multiply constants within an expression. This is one expression. You should multiply the 2 times the 5. So that tells me you know it's this times this times this times this times this. And this whole thing is added to this whole thing. So really, the only thing in 2.6 is the chain rule. Derivative of the outside value weight of the inside times the derivative of the inside. And then we just do a bunch of examples of polynomials and trig functions because that's the only thing we know how to differentiate right now. Eventually we're going to learn e to the x and ln of x and some widen our range of functions we can differentiate. But we're still going to be able to apply the product rule, the quotient rule, and the chain rule within those functions. Old final, this one's a good one. This is a final exam potential question. And really there's 3 functions going on here. So what's the derivative of this function? So what's the derivative? What's the outsidemost function?
Half x to the 4.
It's not half. The outside function is sine.
Whole sine.
So what's the derivative of sine? So I would have y prime is cosine square root of x to the 4th plus 3 times, and then what's the derivative of the inside? Very good. And then what's the derivative of that inside? 4x cubed, right? So now simplifying, I could potentially simplify it. Your book your book, the final exam says don't simplify, so this is perfectly fine. If you did simplify it, you weren't necessarily going to lose points.
So are we using the product rule
Here we're using all chain rule.
here?
The derivative of the outside is cosine, evaluated at the inside, times the derivative of the inside. So times the derivative of the inside, which would be 1/2 its inside to the minus 1/2. So the derivative of its inside would be 4x cubed.
So we can use the product rule right there.
There's no function times a function. It's a function within a function. The product rule only works when you have a function times a function. The quotient rule works when you have a function divided by a function, and the chain rule works when you have a function within a function.
If you were to derive that, yes,
If you would take the second derivative?
Yeah.
Yeah, if you have to take the second derivative, you're going to want to simplify it and use a combination of product and quotient, because you have a function times a function times a function, and it will be a little bit easier if you have a function times a function divided by a function. Yeah, if you have to do it again, you're going to have to use the product rule.
But we will never take the second derivatives unless we are asked to do so.
Correct. If I say find the second derivative, you will have to find the second derivative. In Chapter 4, we'll learn about concavity, and if I ask anything about concavity, that has to do with the second derivative. So you know how we'll learn to take, okay, concavity means I need to take the second derivative and deal with that. So. And in Chapter 5, we'll learn about rectilinear motion, which has to do with position, velocity, and acceleration. So if I say anything about acceleration, you know that's related to the second derivative. And then at the end of Chapter 5, we'll learn integration, and we'll learn to go backwards. If I give you an acceleration function, you can tell me the position function by using the antiderivative. Question?
So do you know that the one I just did is just one function because there's no variable in front, but the other one, there's two functions? Like, how do you know?
Well, this is a function times a function, right? So the overall form is the product rule, which is a function times so the derivative of the first function, hold the second one, plus the derivative of the second one, hold the first, so you have that plus in there. Here is a function within a function. So it's the chain rule. So if there was an x out front, I would have to use the product rule, and this part would just be the derivative of the second function. This is just the derivative of this function. I could do the example y equals x times sine of the square root of x to the fourth plus 3. And that would be the derivative of the first function, 1, hold the second one, plus x times this function, because this is the derivative of just that. Does that make sense? So this one here equals basically f prime g plus g prime f. If I call this f, and I call this one g. But here I only have one function I'm dealing with. It's a function within a function within a function. So that's chain rule. Question?
If it was just y equals sine squared of something in parentheses, what would that be considered?
Sine squared of something in parentheses, or sine of something squared?
Sine of something squared.
That's still considered a chain rule. So let's say y equals sine of x squared like this.
Or I was thinking the sine squared of x.
So you're thinking y equals sine of x squared? These are both chain rules. What's the derivative of sine of x squared?
So you need
Cosine. Right? And then what's the derivative of this function?
so 2 sine.
Right? So 2 sine of x to the first power times the derivative of sine, which is cosine. Here, it's the derivative of the outside function, which is sine. It's the derivative of sine is cosine. Evaluate the inside times the derivative of the inside. Question?
On that second one, if it was like 2x,
If this was 2x,
yeah.
then this would be 2 sine of 2x times cosine of 2x times 2.
She did outside function first.
I will not see you tomorrow, right?
Do the derivative of the outside.
And you will take your exam before, or your quiz before Sunday at 11 p.m.
So that's what you're changing it.
Just talking with this one really quick.
Yeah,
I'm
let's-
still not